My name is Sarah van der Moosdijk. I'm a machine learning specialized partner solutions architect here at AWS. Hopefully, you're watching this session because you're interested in learning how to build custom computer vision models. And I have a little bit of a confession to make here. I'm actually more of an expert in natural language processing than I am in computer vision. But about 6 months ago, I found myself working on a very different type of language. So, were you able to understand what I said in that video? Even if not, hopefully you at least noticed that it was sign language, specifically Australian Sign Language. So about 6 months ago, I found myself working on a project to try and build a tool which could translate from sign language into written English. Now, if anybody watching this is actually a fluent user of Australian Sign Language, I do apologize. I'm only a beginner in this language. But if you don't know much about sign languages, a couple of facts for you. We believe there's about 300 estimated sign languages in the world, so Australian Sign Language is just one of those. And we actually use the term Auslan to refer to Australian Sign Language. It originated around the 19th century when it split off from British Sign Language, known as BSL, and it has two major dialects, a northern dialect and a southern dialect. Auslan is actually a very complex language, so meaning comes from several different factors. The shape of the hand is really important, but also the position of the hand in relation to the rest of your body. The movement of the hand is important, your facial and body expression, but you can also use the space around you to really illustrate what's happening and to provide more meaning to what you're saying. So it's a very, very complex problem, which makes it a really interesting problem to solve with machine learning. And when we started on this several months ago with a small team of people, we were very excited and we had loads of ideas for how we wanted to approach this problem. We were thinking video classification, action recognition, pose segmentation, sequence to sequence, and we fell into the trap of starting with the more complex models and therefore the more interesting ones for us. And finally, as the deadline was approaching, we still didn't have a working model. So we came to a point where we decided, okay, will it be possible for us to simplify this problem? What if, instead of working on videos, we could actually make this work for image classification, which is much, much simpler? So that's what we did. On this slide, you see examples of my image training data. So we built a script which actually extracts 9 keyframes from a video of somebody performing a sign. It arranges these frames in a 3x3 grid. And this image is actually what we use for our image classification algorithm. Now, luckily for me, I had 64 wonderful colleagues who agreed to help out to create training data. We ended up supporting 12 signs, short words and phrases, things like hello, how are you, pleased to meet you. And we ended up with a complete total data set of 764 images. So once we had our images, we then had to look at how we were going to build our image classification model. We ended up using the default PyTorch environment provided by Amazon SageMaker, and we applied transfer learning on a ResNet 18, a pre-trained ResNet 18. If you don't understand anything I just said in the last 2 sentences, don't worry. You really don't have to understand the details in order to follow along with this session. But basically, it took us around 4 months of work, 148 training jobs, of which 3 hyperparameter tuning jobs, 49 training hours, and we finally achieved an accuracy of about 83%, which is pretty good. Now, 4 months might seem like a lot, but keep in mind that this included, gathering all of the training data, and keep in mind that I'm not necessarily an expert in computer vision and hadn't really worked with these algorithms before. So let's take a look at how we actually built this in SageMaker. So I'm going to show you how we built the first version of our sign language demo in SageMaker. Now, don't worry if you don't understand all of the detail. I am going to walk through the code very quickly. It's just to really give you an idea of the amount of work that we put into it and the amount of code that we needed in order to get this running. Now, I chose to use PyTorch in order to apply transfer learning on the ResNet 18 model. But you can really use any deep learning framework that you prefer, such as TensorFlow, MXNet, or any one that you're comfortable with. So let's take a quick look at the code. What you see here is my training script, and I actually took it from a PyTorch tutorial on transfer learning. And really what it does is relatively simple. Over here, we have some methods in order to save the model and save the classes to disk. But really, the most important method that I want you to look at is the train method. It does a couple of things. First, it will load in our data, transform it, and put it into a dataset for us to use. Next, it shuffles and splits the data into training and validation sets. Then we go ahead and load the pre-trained ResNet 18 model from the PyTorch library. And all of the other code that you see in this file really just starts up the neural network that we want to apply transfer learning to and goes through the training loops and the different epochs. So this is the training script. The next script I want to show you is the serve script, which is really just the script that we use during inference once the endpoint is up and running. So this is a much shorter script. It only has a couple of methods. First, we have the model fn method, model function, which really just loads the model from the location where we saved it. Then we have the input method here, which takes the input from the API call and transforms it in such a way that we can then feed it into the model. Then down here we have the output method, which takes the answer returned by the model and again formats it in such a way that it's just a little bit easier for us to read. So this is the inference script that we use. Finally, I have this Jupyter notebook here to show you how I actually apply these scripts in Amazon SageMaker. So the first cell here just shows you very high level how we run hyperparameter tuning. So we actually applied tuning to multiple hyperparameters in this case. We point it to our training script over here, and then we can go ahead and run that through SageMaker, which will spin up all the necessary resources in order to complete the hyperparameter tuning. Once the hyperparameter tuning is finished, SageMaker can helpfully display this table with the results. And the top row right here, the one with 80% of final objective value, is our best performing model out of the hyperparameter tuning jobs. So this is the one that we'll actually use to deploy the endpoint, which is what the next cell of code does down here. Once the endpoint has started up, I then go ahead and apply inference to all of the images in my test set. So here you can see that I had an image where the correct label was cat, and the model actually predicted that the sign was cat with a 99% confidence, which is great. Using the results from my test set, I then generate a confusion matrix, which if you know how to read this, this is a pretty good result. It's quite positive. If you're not sure how to read this, don't worry. I will explain things like confusion matrices, precision, recall, F1 score a little bit later in this session. And finally, at the bottom of this notebook, I calculate the precision, recall, and F1 score for each label separately, which is what you see in this table, as well as the macro average precision, recall, and F1 score over here at the bottom. And as you can see, the results are pretty positive. So these results were pretty good, and we were actually able to take our demo to reInvent last year in December and try it out with a live audience where it performed extremely well. So we were very happy with that. Now, at the same event, at reInvent last year, the Amazon recognition team announced a new feature called Custom Labels, and I'd like to dig into this new service a little bit deeper. If you're not familiar with Amazon Recognition, it's a service which was launched in 2016, and it allows developers and customers to easily add computer vision features to their applications. It works on images and video, and it allows you to detect objects, scenes, faces, inappropriate content, and text in those images and video. Now, Amazon Recognition is great, but it's sometimes not specific enough for your particular use case. Let's take the example of a car company. They might have images coming in of used cars that need to be sold on their marketplace, for example. And they might want to not only detect if there's a car in an image, which the pre-trained version of Recognition would be able to do, but they might also want to be able to detect the make and model of the car. And this is where the pre-trained version of Amazon Recognition isn't going to be specific enough. To address this customer pain point, the Amazon Recognition team launched a new feature called Custom Labels. This allows you to train your own custom computer vision models on your own data, but is still as easy to use as Amazon Recognition was. You really don't need any machine learning expertise. It's as simple as using the console or using the SDK, providing your data, and Amazon Recognition will take care of choosing the right algorithm, doing the hyperparameter tuning, and starting up an endpoint for you. So if we go back to the example of the car company, they could now, as well as using the pre-trained recognition model to detect cars, they could also train a custom recognition model to detect the make and model of every single car. And all they really have to do is provide the data. So when I heard about this new service and this new feature, I figured, well, this is interesting. What if I tried using it for my sign language demo? So let's take a look at the results. So here are the results of applying Amazon Recognition custom labels to my sign language dataset. Remember, it took me around 4 months and 49 training hours in order to build the same thing in SageMaker, keeping in mind that I did have to do all of the work of gathering the dataset and pre-processing it from video into images, which I didn't have to do in this case. Still, it only took me about an hour to recreate my model from SageMaker in Amazon Recognition custom labels. And it actually gets slightly better results if you look at the F1 score over here, the average precision over here, and the overall recall here. Total training time was only about 45 minutes. So this is a really great result, and possibly a slight dent to my ego. But if you think about it, it makes complete sense. Amazon Recognition has a team of world-class computer vision experts in order to build this service. So it really makes sense that the resulting model on the same dataset performs really well. So let's take a look at Amazon Recognition custom labels and how you can get to this point with your own data. So to use Amazon Recognition custom labels, you are going to have to provide it with a dataset. And there's a couple of different ways in which you can do this. If you already have your data stored in an S3 bucket, then you can simply upload the data from that Amazon S3 bucket into Amazon Recognition. If you happen to have used Amazon Recognition custom labels before, and you have an existing dataset within the service, you can also create a new dataset from this existing dataset. If you do have the images stored on your local computer, there's also an option to simply upload them directly into Amazon Recognition. And finally, if you have images that aren't yet labeled, you may want to consider using Amazon SageMaker Ground Truth to first label your images, store them in an S3 bucket, and then upload this as a dataset to Amazon Recognition. So let's take a look at how I did this for my sign language demo. So in my case, I already had my sign language data uploaded into an Amazon S3 bucket because I was using SageMaker previously. And this is what my S3 bucket looks like. So right now, we're looking at a directory that contains my training data. And I divided all of the images for the training data into separate subdirectories, where the name of the subdirectory indicates the label for that particular image. So if I click, let's say, on the cat subdirectory, you'll see here that I have all of my images with my colleagues signing the sign for cat. Now, the advantage of storing your data like this is that Amazon Recognition can actually read the folder structure and use the names of these folders to automatically label your data. So you don't have to go through any extra work in order to get the labels. This is a very common way of storing data for image classification use cases. But if you are going to be using object detection or semantic segmentation, then this isn't going to work, and you are going to have to use Amazon SageMaker Ground Truth instead. If you're not familiar with Amazon SageMaker Ground Truth, it's a service which makes it easier and saves you a lot of time and effort in order to label your data. The way that it works is you provide it with your unlabeled data, and you have a set of human annotators that you want to label your data. But as the data is being labeled by the human annotators, Amazon SageMaker Ground Truth will actually train a machine learning model in the background. This machine learning model will improve over time as more and more labels come in. And finally, when the confidence is high enough, it will actually take over part of the labeling effort which no longer has to go to the human annotators. When this happens, and if the confidence of the model is high enough for a particular label, it will simply send that label on its way. But if the confidence is too low, the model will send the image to a human annotator anyway, and that label generated by the human is then returned to the model in order for continuous learning to happen. Now, when you are using Amazon SageMaker Ground Truth in order to label your data, it will generate what's called a manifest file. And this is its output. A manifest file contains all of the information on where to find the image, as well as the label that you've attached to it. On the slide, I've included a small portion of a manifest file as an example. So a manifest file is a JSON lines file, which means it has one JSON object per line. And the slide shows just one of these JSON objects. This represents one image with its corresponding label. So let's take a closer look. It might seem a little bit daunting at first, but if you go through it, it's actually pretty simple. The first line is what we call the source reference. And this is really just the S3 location of the image that you're currently looking at. So that's pretty simple. Next, we have what is really just an identifier. So note that the name of my key value pair here, or the key itself, is called signs. And that's because this particular manifest file is for my sign language dataset. But you can actually change this key to be more relevant to your particular use case. If we think of the car company, the key could be make or model, for example. So the key is really up to you, and this line is really just an identifier. That's all it is. Next, we have the start of a sub-object within this JSON object. And here, again, all I need you to look at is just the key. In this case, it's called signs metadata, again, because it's for my sign language project. But you can also change this name here to make it more relevant to your particular use case. Everything within this sub-object relates to the label that you've assigned to that particular image. So the very first line within this sub-object is simply the class name. This is your label. So in this case, I had an image of one of my colleagues using the sign for hello. Therefore, the label is simply hello. Next, you have the confidence. If you have a human labeling your data, the confidence will usually be 1. But if the machine learning model within Amazon SageMaker Ground Truth took over and did the labeling, the confidence can be anywhere between 0 and 1, hopefully at the higher end of that scale. Next, you have the type of labeling task that you're using in SageMaker Ground Truth. There's various different tasks that it supports. In this case, we're doing image classification because we take an image as a whole and assign a label to it. But you also have options like object detection, semantic segmentation, text classification, and more. This value will stay the same for your entire dataset because you're really only using one type of labeling per dataset. Next, you have a flag which indicates if this particular label was generated by a human or if it was generated by the machine learning model within SageMaker Ground Truth. And finally, you have the creation date, the exact date and time at which this particular label was generated. Now, notice that I've actually highlighted the top 4 lines in blue, and that's because these are really the most important lines that I want you to focus on. The rest of the information in white, it's useful to have, but it's not going to be crucial to training your machine learning model. So really make sure that the information in blue is correct. Make sure you have the correct location to your image, make sure that your identifiers are all correct, and make sure that your labels are correct. So that's really the most important bit. Now, if you are using SageMaker Ground Truth, it will generate this manifest file for you. But now that you understand how it's built, you can imagine it would be pretty simple to create a piece of code that can generate it if you're not using SageMaker Ground Truth. And actually, if you're going to use the same method of uploading data that I used, by storing your data in an S3 bucket in folders that indicate the label, then Recognition Custom Labels will go ahead and generate this manifest file for you as well. So let's take a look at the manifest file that it generated for my particular use case. So here you see the manifest file which Amazon Recognition Custom Labels has generated for me based on how I had stored my data into these subdirectories that I showed in the previous demo. As you can see, I have lots of different lines, and each line looks very similar. Each one is a JSON object. So if we look at one of these lines in a little bit more detail by making it easier to look at, you can now see that we have a very similar structure to what I was showing on the slide. The first line here is the source ref, which is the location of that particular image in my S3 bucket. We then have the identifiers that I was mentioning before, and we have all of the information related to the actual label, which in this case was cat. Now, you might notice that we do have one additional key value pair in this JSON object. That's because the key value pairs that I was showing on the slide are all of the key value pairs which are mandatory. You can actually add additional information to each JSON object if that's something which is useful for your application. But in general, you should really recognize the structure that I'm showing in this file generated by Amazon Recognition as compared to the structure that I was showing on the slide. So once you've uploaded your data to Amazon Recognition custom labels, the next step is to actually train the model. And this is super easy. It's literally the click of a button. You pretty much point Amazon Recognition to your training data, you point it to your test data, you give the training job a name, and that's all. Amazon Recognition will take care of analyzing the data, formatting the data, choosing the right algorithm, doing the hyperparameter tuning, and everything afterwards. So it's really, really straightforward. Once it's finished training, you'll have a couple of evaluation results that you can use to figure out how good your model actually is. These results will be shown in the AWS console, but you can also access them through the SDK. Now, here you may need a little bit of machine learning knowledge in order to understand what these results mean. They're provided to you as precision recall F1 score, as well as the macro average precision recall and F1 score. So if you're familiar with machine learning and you've been in this field for a longer period of time, you'll know what these mean. But if you're new to this field, I'm going to try to demystify these terms just a little bit. I like to use Venn diagrams to explain what these terms really mean. So let's imagine that everything within the gray box is our data. Everything within the blue circle is the data that we know to be true. And everything within the orange circle is the data that our model thinks is true. So when you do inference and the model says the data is true, it will end up in the orange circle. So let's take a look at how this works. Everywhere that the circle overlaps, these are called our true positives, because it means we know the data is true and the model thought it was true, predicted that it was true. If you look at everything that's within the gray area of the rectangle but outside of the circles, these are our true negatives, because it's the data that we know to be false and the model correctly predicted that it was false. If you look at the blue circle again, and this time everything within the blue circle except the overlap, these are our false negatives, because it's data that we know to be true, but the model predicted it to be false. So here the model was incorrect. And similarly, if you look at everything within the orange circle, but not in the overlap, these are our false positives. So it's data that we know to be false, but the model actually thought it was true. Now, I can imagine that it's a little bit difficult to understand with an abstract problem of true or false. So let's take a look at this with a real-world problem. Let's imagine that you have a spam classification model. An email comes in, it goes through the model, and if the model classifies it as spam, it gets sent to the junk folder. If it classifies it as an important email, it'll simply get sent to your inbox. So again, let's take a look at this. Everything that is within the blue circle is the emails that we know to be spam, whereas everything in the orange circle is the emails that the model predicts to be spam. So our true positives are where the model correctly predicted that an email was spam. Our true negatives are where the model correctly predicted that the email was not spam. Our false negatives are the emails that we know to be spam, but the model predicted that they were not. And our false positives are the emails that we know not to be spam, but the model predicted that they were. So I'll give you a moment to think about this, but in this particular use case, would you want less false negatives or less false positives? Hopefully, if you think about it for a moment, you'll come to the conclusion that in this case, you would want less false positives. These are the emails that we know are not spam, but the model did mark them as such, which means they ended up in the junk folder, even though they really shouldn't. And I don't know about you, but I don't really check my junk folder all that much, so I could miss some important emails if I had false positives. So here, because we want to decrease the number of false positives, the metric that we want to look at is precision. I'm not going to give you the exact formula because it's really easy to look up and understand for yourself, but precision is pretty much a formula which measures the true positives and the false positives. So in this case, we really want a high precision for this particular use case. Let's take a look at another use case just to make it clear. Let's imagine that we have an algorithm which analyzes an X-ray from a patient and tries to determine if the patient is ill or healthy. So everything within the blue circle, these are the patients that we know to be ill. Everything in the orange circle, these are the patients which the model predicts to be ill. So again, let's have a look at this. Our true positives, everything within the overlap, these are the patients that we know to be ill, and the model predicted that correctly. Our true negatives, everything in the gray rectangle area outside of the circles, these are the patients that we know to be healthy, and again, the model predicted that correctly. Our false negatives in this case, these are the patients that we know to be ill, but the model predicted that they were healthy. And our false positives in this case are the patients that we know to be healthy, but the model predicted that they were ill. Hopefully it's clear that in this case, we actually want to have less false negatives. These are the patients that were ill, but the model predicted that they were healthy, which is definitely the worst in this case, and it's what we want to avoid. So if you want less false negatives, the metric that you have to look at is recall. And again, I'm not going to give you the formula. It's really, really easy to look up, but it's really just a measure of the true positives with the false negatives. So in the case of spam classification, we wanted a high precision. And in the case of the patient classification, we wanted a high recall. But why are we looking at these two metrics separately? Well, the reason is that these two metrics are often opposing forces. Generally, if you increase the precision, your recall is going to drop, and the other way around. Now, if you do have a use case where you don't really have a preference for either recall or precision, that's when you can try to use the F1 score. And the F1 score is really just a harmonic mean between the two, between precision and recall. So hopefully this helps you understand a little bit better what these metrics mean. And now what we're going to do is we're going to take a look how this actually reflects on my own use case of sign language. So here you see the results of the model that Amazon Recognition Custom Labels trained for my sign language dataset. And now that you understand F1 score, precision, and recall, you hopefully notice that these results are not bad. So at the top, you see the macro average F1 score, recall, and precision. In the table below, Amazon Recognition will show you the same F1 score, precision, and recall, but this time for each label individually. Here you can see that the label cat performs particularly well, keeping in mind that I'm only testing it on 5 images, which is not a massive test set. Now, what I'd like you to look at on this page in particular is the assumed threshold column all the way on the right of the table. This assumed threshold is a threshold which Amazon Recognition will calculate for you. And the way it works is as follows. If you have an image that you send to the trained model, the model will return a label that it thinks is likely, as well as a confidence level. So let's say that in this case, we send an image of somebody signing cat, and the model returns the label cat with a confidence level of 60%. Now, because 60% is higher than the assumed threshold of 31%, the model will go ahead and return that label. If, however, the confidence level was below 31%, which is the assumed threshold for cat, then the model would actually not return the label cat. So why is this assumed threshold important? It's important because this is what you use in order to control your precision and recall metrics. If you increase the assumed threshold closer to 1, your precision is going to increase, but your recall will most likely drop. So you can really use these thresholds, which you can actually adjust when you make an inference call, in order to find the right balance between precision and recall for your use case. The assumed thresholds calculated by Amazon Recognition are simply what it recommends and it thinks is best for each label, but you can adjust this for your own use case. Now, Amazon Recognition also allows you to look at the results of your model in a little bit more detail. So here you can see the results for my test set. We have an image of Stephanie here signing cat, and we can see that the model returned the label cat as a true positive, so it got cat correctly, and it had a confidence of 98.5%, which is far above the assumed threshold, and it was therefore able to return this label. So this is an example of a true positive. Now, if you notice in the filtering box on the left, I have true positives, and false negatives, but no true negatives. This actually makes sense because I don't have a single image in my dataset where somebody is not signing. So really, there's no such thing in my use case as a true negative, and therefore there's nothing I can filter on. But let's take a look at the false positives and the false negatives. Here, we see an example of Dave signing 8 o'clock, and you can see that it has both a false positive and a false negative. So let's understand what this actually means. So the model, when it was fed this image, it did actually think that the label 8 o'clock was one of the potential options. But the confidence level that it returned for 8 o'clock was 30.8%, which is below its assumed threshold, and therefore it didn't end up returning 8 o'clock, even though this is the correct label. And this is what is a false negative in my particular use case. A false positive in this example is grandfather. So the model thought that grandfather was another potential label, and the confidence level that it has for grandfather of 25.6% is above its assumed threshold. So in this case, the model returned grandfather, which is incorrect, therefore a false positive. It did not return 8 o'clock, which had actually been correct. Therefore, this is a false negative. Using this user interface provided by Amazon Recognition really allows you to understand what the true positives, false negatives, and true negatives mean in the context of your own use case. So now you know how to evaluate how good your model is from the console. But Amazon Recognition also saves these results into files, into an S3 bucket. So if you prefer, you can also use the SDK to get the results directly from those files. The two files it uploads are a summary file and a manifest snapshot, and it pretty much contains all the information that you just saw in the console, as well as an additional confusion matrix. So let's take a quick look at the summary file that Amazon Recognition generated for my sign language use case. So here you see the summary file that has been generated by Amazon Recognition custom labels after training a model on my sign language data. Again, it contains all of the information that we just saw on the console, but in addition, it also has a confusion matrix all the way at the top here. This will be very similar to the confusion matrix that you saw me generate in the Amazon SageMaker notebook. So all you have to do is grab it from this file and visualize it in order to take a look at it in more detail. If we go further down in this file, you'll see that it provides the other metrics as well. So here in the middle, we have the macro average, F1 score, precision, and recall for all of the labels as a whole. Below that, it shows all of the unique labels that it found in your dataset, as well as the number of testing images and the number of training images that were involved in this particular model. Finally, at the bottom of the file, you will receive the individual F1 score, precision, and recall, as well as the assumed threshold calculated by Amazon Recognition for each label separately. So now you know everything that you need in order to properly evaluate your model. If it's not good enough, you can simply go and edit the data and perhaps retrain it. But there's also some options to actually have a feedback loop built in once you have a model that's trained. The Amazon Recognition team has provided an open source model feedback solution which is available on GitHub. In fact, I've included the link in the extra resources that will be attached for this session. What it allows you to do is once you have a trained model and you're sending images through this model, you can use the model feedback solution to then send the results of the inference to an Amazon SageMaker ground truth job, where human annotators can look at the results and provide feedback. They can perhaps edit them, or they can accept the answer as the correct one. This is just another way in which you can ensure that your model that you're using is really correct and that you're happy to use it further. So hopefully, once you've finished evaluating your model, you'll have a model that you want to deploy to production. Amazon Rekognition actually takes care of starting up an API endpoint for you, so you don't have to worry about any of that. But you do need to start and stop the endpoint when you plan on using it. This prevents you from paying for resources that you're not actually using. So always remember to just start your endpoint when you're planning on using it, and don't forget to stop it when you're finished. Now, in terms of pricing for the endpoint, you're actually paying a certain price per inference unit per hour. An inference unit really just represents the amount of throughput that the endpoint can accept. In this case, one inference unit represents about 5 transactions per second. Now, whenever you're starting up an endpoint, you can determine the minimum TPS value that you want the endpoint to have. And this is really just the minimum throughput that your endpoint will have at all times. But don't worry, if you do experience a peak, Amazon Rekognition actually takes care of the auto-scaling for you. It will scale up the resources behind the endpoint to handle the additional load of incoming data, and once it's finished, it will actually scale back down to the minimum TPS value that you set for your endpoint. We always recommend starting with the lowest TPS value of 1 for your endpoint. You can then monitor how much is actually coming in through CloudWatch and adjust the minimum TPS based on that. So once you've started up your endpoint, there's 2 different ways that you can actually send an image in order for inference to happen. Amazon Rekognition accepts the images either as a base64 encoded byte array, or if you have the image stored on an S3 bucket, you can simply provide the location of the image within the S3 bucket. Now, remember during the demo that I showed the assumed thresholds which Amazon Rekognition calculates for every label? Well, when you actually make an inference call, you can add an additional parameter to adjust the threshold that's being used. And this is how you control the precision and the recall of your model. You can change this with every single inference call. And that's really all you need to know on how to use Amazon Rekognition. So in order to close off, you might be wondering, when do you use Amazon Rekognition, or when should you use Amazon SageMaker? I've used both successfully for my sign language project, so what are the differences? Let's take a look at a quick summary. Amazon SageMaker is a really powerful tool that supports advanced machine learning use cases. Anything you can build in MXNet, PyTorch, TensorFlow, whatever deep learning framework you're most comfortable with, you can build in Amazon SageMaker. Amazon Rekognition Custom Labels currently only supports images, and it supports 3 use cases: image classification, object detection with bounding boxes, and semantic segmentation. So if your use case does fall into one of these 3 areas, then it's actually easier to use Amazon Rekognition. It requires no machine learning expertise, but even for advanced data scientists, it makes for a really fast experimentation tool in order to build your first baseline model. So really use Amazon Rekognition if you have limited experience with computer vision, or if you just want to get a model up and running very quickly. Now, there's 2 more reasons why you would want to choose Amazon SageMaker currently over Amazon Rekognition. One is if for any compliance or regulatory reasons you need full control over the environment and the algorithms that you're using, then it's probably better to choose Amazon SageMaker. Amazon Rekognition will not reveal the underlying algorithm that it's using or the hyperparameters that it chose after tuning. So again, if for compliance reasons you need this information, then go ahead and build your own in Amazon SageMaker. And finally, although the pre-trained version of Amazon Rekognition is currently available in the Sydney region, the custom labels feature is unfortunately not yet available. So if your data needs to stay within the Sydney region for data sovereignty reasons, then currently you will need to use Amazon SageMaker. So I hope that helps you make a choice, and I hope you choose to use one of these 2 wonderful services. Now, if you're interested in the sign language demo, which I've been talking about repeatedly throughout this presentation, we do actually have the first version of our MVP code out on GitHub. I've included the link in the additional resources for this session. So if you want to build your own version of this demo for a sign language of your choice, I'd really love to see what you do with it. Have fun. And finally, I just want to thank you for attending this session. I really appreciate that you took the time to listen to me talk about this project. Please fill out the survey. It would really mean a lot to me to hear your feedback, and I hope you have a great day.